Hello, everyone, and welcome back to Maths Zone African Motives. So, as we continue, we want to continue with the topic momentum, impulse, and collisions. But what I've done today is that I've brought you a question from a question paper. So I just took a full question from a question paper that is on the topic momentum, impulse, and collisions. But before we can dive deep into that question, we get to see what is it that we were expected to do, what is it that we are expected to know in terms of momentum, the definitions, the calculations. I want us to start by doing, or else start by defining what collisions is, what is a collision. Then after, I want us to look into different types of collisions, which is elastic, inelastic, and purely inelastic collisions, so that we can be able to answer questions to do with what? With collisions. So let's start by defining what collision is. So a collision occurs whenever we've got two or more objects. So whenever we've got two objects, and then these objects, they get to interact like this with each other for a short time, for a short time of period. You would get to see that these two objects, they get to exert forces on each other. Let's take, for example, a car is being driven maybe towards the right, and then it gets to collide maybe with a truck that is going towards the what? The left. So what you see that will happen is that this car and this truck, they will interact for a short period of time, and then they are going to exert forces on each other. That is what we refer to as a collision. I'm sure you have heard people refer to some accidents as head-on what? Collision. It was a head-on collision. That is what they actually mean. So since we now know what a collision is, I now want us to look into what? Into different types of collisions. So you will see that whenever two or more objects collide, it's either the objects, they would actually get to separate, or else the objects, they will get to what? They'll get to stick with each other, and then they move together. At some instances, when objects collide, you would get to see that the other object would actually get to deform in shape. Like, for example, when a small car collides with a big truck, let's say a small car collides with a big truck, what would actually happen is that you would see that the smaller car is the one that gets deformed. In most instances, when a small car maybe hits on a what? On a truck, it gets deformed. What are we saying? That we are saying that the shape of this car would actually get to change. So when that happens, we say that that is an inelastic collision. Why? Because you would see that whenever there is a collision, there is conservation of momentum. But when we have an elastic collision, this is when two objects bump into each other and then they separate without any of these objects changing shape. Therefore, we will see that our kinetic energy is always conserved in that scenario. So for elastic collisions, our total kinetic energy is conserved. While when there is an inelastic collision, this is when we say that whenever two objects collide and there is an inelastic collision, you would see that either one of the car would get deformed or both of them. So we are saying some of the kinetic energy will be transformed into what? Would be transformed into the energy of deformation. What causes this object to deform in shape? It is energy that is from this kinetic energy. And at some point in time, you can actually hear a loud bang. So some of the kinetic energy would be transformed into sound. So whenever there is a collision and we get to hear some sound, maybe there is a loud bang or else some sound, there is change in shape, just get to know that that is an inelastic collision. Why? Because the total kinetic energy will not be conserved. But for all our collisions, total momentum would be conserved. So the difference between elastic collision and inelastic collisions is that when there is an inelastic collision, you would see that kinetic energy would be conserved. That means that the two objects would collide with each other and then they separate elastically, meaning to say that you won't hear any sound, there won't be any heat produced. These two objects, they won't get to what? To stick with each other. There won't be any change in shape, but once there is inelastic collision, either one of the object's shape will change or else both of the shapes will change. You would hear a loud sound or else there will be heat generated due to the what? To friction. So we are saying our kinetic energy, some of it would be converted to what? To sound, and then some of it would be converted to what? To heat. So our total kinetic energy won't be conserved. And then where we have what we refer to as perfectly inelastic collisions, this is when you get to see that these two objects get to stick with each other and then they move together. Whenever two objects collide and they stick together and then they start to move whilst they stick together is what we refer to as a perfect inelastic collision. And there we know that momentum is always conserved, but maximum loss of kinetic energy occurs. That means that our total kinetic energy will be lost. So if that is the case, now we now know how to differentiate between an inelastic and a elastic collision. And we now know how to differentiate between any other collisions and perfectly inelastic collisions. Now let's look at the question that I said that I brought. So this was a question from a question paper from what? From March 2020. I took this question paper from March 2020 from one of the provinces, and it was on momentum impulse and collisions. The question was saying the diagram below, which is this diagram, shows two sections, which is PQ and QR. So that is from P to Q, and also the other section that is from Q to R, which is a horizontal surface, and it is a flat surface that is smooth from P to Q, while section QR is rough. So what we are having here, we are having a horizontal flat surface where from P to Q, here we have got a what? A smooth surface. And then here we have got a rough surface. And then they go on to say that a 5.5 kg block moving with a velocity of 4.5 meters per second to the right, which is this block, collides head-on with a stationary 3.5 kg block. After the collision, the two blocks stick together and move to the right past point Q. So this one is stationary, whilst this one is going that side. They collide head-on, and then after the collision, they stick with each other, and then they move to the right past point Q. So what is it that we are saying? So we are saying that our objects, they will collide head on, and then after head on, they will stick with each other like that, and then they get to move past this point, which is towards the right, towards the point R. After that, they are said to say that the combined blocks travel for 0.6 seconds from point Q before coming to a stop at point R. So the combined blocks travel for 0.6 seconds from point Q, which is point Q, before coming to rest. The question is saying, state the law of conservation of momentum in words. So we know that the law of conservation of momentum states that in an isolated system, or else in a closed system, the total linear momentum is conserved. Just allow me to rub so that I can change the font of my pen there, because some of my words, they are not coming out clearly. So we say that the law of conservation of momentum, it states that in an isolated system, so in an isolated system or a closed system, so isolated just means what? Closed. The total linear momentum linear momentum, the total linear momentum is conserved. That is what it means there. The total linear momentum is conserved. Now, they're now saying calculate the magnitude of the velocity of the combined blocks at point Q. So they now want us to find the velocity at which these two combined blocks will pass this point moving at. So we want final velocity of these two objects, because initially this one is at rest and this one is moving at that velocity. So what we usually do here, we now get to apply this law of conservation of momentum here. So what I advise when we get to this stage is that first thing is first, you need to draw the sketch of what is happening, which is the diagram of the scenario that you're seeing here. So we are being given that this is the what? The 5.5 kg block, and then we are told that this is the 3.5 kg block. And this is moving at 4.5 meters per second, going in that direction. And this one is having a velocity of 0. That is before collision. After collision, these two objects, they stick together and they move towards that direction. That is what we have been told. And then we now need to find the final velocity there. So the mass, the total mass of these two will now be equal to what? To 5.5 plus 3.5 kgs. So after this, we were supposed to have defined our direction, but our direction is already given. We now get to apply the law of linear momentum, which says that the total linear momentum before or initially should be equal to the total linear momentum after, or else final. So what is the total linear momentum before? Allow me to now just get to wrap this. So now we get to say that total linear momentum, it is linear momentum of this object first. That is linear momentum initial, or else let me get to say linear momentum of object 1. We know that momentum is represented by the letter P, plus momentum of object 2 initially being equal to momentum of object 1 plus momentum of object 2 finally. And we've been told that these, they actually get to stick together. So here I would say mass of object 1 times velocity of object 1 plus mass of object 2, velocity of object 2 initial, is equal to mass of object 1 plus mass of object 2 times the final velocity that we are looking for. After that, we start substituting what we know. So we know the mass, which is what? 5.5. And we know the velocity here, which is 4.5. And here we know the mass 3.5 and the velocity is 0 equal to. Now we now get to add our two masses. We now get to add our two masses, which is to say that 5.5 plus 3.5, and then this is where now we are saying we are looking for our final velocity. That being the case now, that being the case, we get to actually get to what? To solve this side and then make VF the subject there. So I'm just going to punch my calculator here to say what is 5.5 and what is what is 5.5 times 4.5. So we can use our calculators there. So here I'm having my answer being 24.75. I've got an answer that says 24.75. That is the answer that I'm having there for this value. So this one is saying 24.75. And then this one would be 0. And then this side, I'm having 5.5 plus 3.5. That is equal to 9. And then I've got VF. So I will divide by 9. And then I will divide by 9. And then these ones, they cancel out. And then I'll be left with that, with V final this side. And then I would say 24.75 divided by 9. And then that would be equal to 2.75 meters per second. So that is the final block. That is the final velocity with which the two blocks would be moving at. That is what we're supposed to calculate here. So our answer here is our final velocity would be equal to 2.75 meters per second. 2.75 meters per second. Now, they're now saying use a calculation to prove that the collision between the two blocks is inelastic. This is what we were just discussing, to say that for an inelastic collision, our total kinetic energy is not conserved. Our total kinetic energy before is not equal to the total kinetic energy what? After. So that is what we simply need to prove there, because we say that for elastic collision, kinetic energy is conserved, but for inelastic collisions, kinetic energy is not conserved. So it means that total kinetic energy before is not equal to total kinetic energy after. So just allow me to use the space below here to calculate that total kinetic energy. So what I'm going to do is I'm going to say 3.3 total kinetic energy before is equal to, I know that kinetic energy is equal to half mv squared. So now total kinetic energy before, it will be kinetic energy of object 1 plus kinetic energy of object 2, which is equal to half mass of object 1 velocity of object 1 squared plus half mass of object 2 times velocity of object 2 squared. Now all I now need to do is to substitute the values that I know there. So now I'm going to say that half of my mass, which is what? My mass is 5.5 times my velocity, which is 4.5 squared, plus half of my mass, which is what? I know that the mass of the second object is what? The mass is 3.5. The mass is 3.5. So the mass of my second object is 3.5 times the velocity, which is 0. So I know that this one will fold to 0. That one will fold to 0. That one will definitely fold to what? To 0. This is equal to 0. So I would be left with, I now need to punch in my calculator. where I'm saying half times 5.5 times 4.5 squared. Now the answer that I'm getting there, it's 55.6875. So I've got 55, 55.6875. This is in joules. This would be in joules. So we know that our energy is calculated in joules. So I'll simply use J to represent our units. So this one would be in joules. So you can actually simply say what? This is the what? The kinetic energy before. Now, I now want to look into kinetic energy after. I now want to look into kinetic energy after. So I'll say total kinetic energy final. That is kinetic energy of 1 plus kinetic energy of 2 at final. Now I would say half. I know that they would combine. These two objects, they will combine to become one object and with their one velocity. So I would have mass of object 1 plus mass of object 2, but the velocity would be squared. So now what am I getting here? I'm going to get half of 5.5 plus 3.5 and then multiplied by what is the total velocity that we found there? We found 2.75 meters of the two objects. That is 2.75. And then I will square it. Thereafter, I now need to find the answer there. So I'm also going to use my calculator while you're also using yours to say 0.5 or half times 5.5 plus 3.5 times 2.75 squared. That is going to give me an answer of what? 34.03125. So the answer that I'm getting here is going to be 34.0315. So in joules. So you can see that now I now have got two answers, which is to say the total kinetic energy before and the total kinetic energy after. So you can see that total kinetic energy before is equal to that value, total kinetic energy after is equal to that value. So these two values, they are not equal. So what you come and do here, you are going to say, you have to come and say total kinetic energy initial is not equal to total kinetic energy after. Therefore, the collision is inelastic. The collision is inelastic. Once the total kinetic energy before is not equal to the total kinetic energy after, you know that the collision is inelastic. That is what we are just supposed to prove there. So now let's go back to our question. Let's see the question that follows. Now, they are now saying, calculate the magnitude of the net force acting on the combined blocks when they move through section QR. So we know that I'll clear my board here so that I can explain some concepts. We have done this to say that net force can actually be given in terms of what? Of rate of change of momentum. We have done that. Net force can actually be given in terms of rate of change of what? Of momentum. So they want us to calculate the net force of the two objects, or else the net force that is acting upon the two objects when the two objects move from P to what? To Q. What is making these two objects come to rest? That is the net force that we want to calculate. But we have been told that these two objects, they move in a time of 0.6 seconds. So now this is where I would come and say that you can apply this theorem that I'm emphasizing here to say that net force is equal to rate of change of momentum. We know that net force can be given by rate of change of what? Of momentum. Where we are saying that this is change in momentum per unit time interval. So our time interval we are given, it's 0.6 seconds. So what we just need to do is to find the change in momentum there. Then we can be able to know our net force. So we also know that change in momentum can be given by mass 1, let's get to say what? Mass 1, V1 initial. Let me just get to write it neatly here. So the change in momentum here, we have got our two objects combined as one, and we have got our two objects combined as one. They are moving with an initial velocity. Now they'll be having a final velocity. So here I would come and say mass 1 plus mass 2 bracket V final minus V initial, where this becomes one object. So we have already said 5.5 plus 3.5. 5.5 plus 3.5 will give you a total mass of what? M total would be equal to 8 kgs. So I would use 8 kgs there times my final velocity minus my initial velocity. That becomes my change in momentum. So this is what I'm going to substitute here. So that is what I'm going to substitute there. So allow me to move it up there. So I'm going to say that my net force from this equation would be equal to 8 times my final velocity minus my initial velocity of the two objects divided by the time taken, which is 0.6 seconds. Now, my initial velocity of the two objects when they are here, it's actually what? This is the velocity that we found here where we said it's what? 2.75 seconds. This was the final velocity, which is velocity at Q, meters per second there. And then now when they get at R, they come to rest. So their final velocity here would be 0. So I'll be having 8. Let me use another pen here. I would use 8 bracket. My final velocity is 0 minus 2.75 all divided by 0.6. That is how you simply calculate your net force there. That is how you simply calculate your net force there. So that what you are going to have here would be 8 times a negative 2.75. Because if say 0 minus 2.75, it will be a negative that over 0.6. And then you can get your magnitude of the what? Of the net force there. And that is going to be, magnitude is, we want the magnitude. That is the size only. We do not care about what? The negative or the opposite, the negative or the positive. We only want the size of the force. That's what they say, the magnitude. Now let's punch in our calculators. We will say 8 times 2.75 divided by 0.6. So I'm getting an answer of 36.66. The answer that I'm getting here is 36.667 newtons. That becomes my net force. So that is what I was supposed to calculate there. So here they said calculate the magnitude of the net force acting on the combined blocks when they move through section QR. So I've used the principle that says net force is equal to the rate of change of momentum per unit time. And I know that the change in momentum can be given by, since the two blocks are combined, they act as one object, and they act as one object at Q and at R. So at Q, they are moving at a velocity of 2.75, and at R, they are stationary. So their velocity is 0. So I would come and say their total mass, V final minus V initial, all over their time taken. That is what I've done. And I've inputted their total mass to be 8, final velocity is 0, because they come to rest at R, minus 2.75 divided by 0.6. And then you get your what? Your final answer there. That is what you would be expected to do. That is what they expect you to do. That is actually questions to do with momentum and impulse and collisions. So let's actually get started with our revisions. Let's read through the notes, and also let's use our previous videos in actually revising through and preparing through for our exams. So thank you so much, guys. Let's meet in our next video, where I would bring more questions to do with momentum, impulse, and collisions.